I thought inference was just a fairy tale, fused with stats and probability. Frequent test approaches made no sense to me, summarizing evidence by P. Then I saw Tom Baines. Now I'm a believer, without a trace of doubt in my mind. I'm a Bayesian. Oh, I'm a believer. I couldn't be now if I tried. I thought likelihood was just the only thing. Turn the crank and get the MLE. What's the use of thinking? Disconnect your brain, play it long and minimize the pain. Then I saw Tom Baines. Now I'm a believer, without a trace of doubt in my mind. I'm a Bayesian. Oh, I'm a believer. I couldn't be now if I tried. Sam's out to get me. That's the way it seems. Fixed effects and forced normality. Then I saw Tom Baines. Now I'm a believer, without a trace of doubt in my mind. I'm a Bayesian. Oh, I'm a believer. I couldn't be now if I tried. Then I saw Tom Baines.
All right. So that was a parody of I'm a Believer, and the band that made that music are all Bayesian statisticians, including Michael Jordan. So the reason I set that up today, because today most of the talk is going to be about HMC, Hamiltonian Monte Carlo, which is the engine of what people use nowadays for posterior approximation in a very famous package called STAN. So I thought that that's a good time to show this video. So today's lecture is the last lecture on approximate posterior inference, approximate inference. So please submit your reading after a week. Also, I talked very briefly about diagnosis of MCMC and how we can make sure that it's converged and all that, but didn't have time to talk about it, so I uploaded a few page from Andrew Gelman's book that's about diagnosis. Please take a look. It will become handy very much when you want to actually use this kind of algorithm, or even in your homework when you want to make sure that your algorithm is actually converging to something meaningful. Okay, so today I'm going to continue with the slice sampling, and at the end I'm going to finish with Hamiltonian Monte Carlo HMC. So a little bit of recap from last time. If you remember, we talked about rejection sampling. The general idea of rejection sampling was that you should use some sort of auxiliary variable that accept or reject the proposal. And the idea was that you want to sample from Px, but you don't have the normalizer. You only have it up to a normalizer. And the example of that is that, for example, when you want to compute the posterior probability of the random variable, you want to compute, let's say, PZ given the data. You don't have it, but it's proportional to your joint likelihood. This is coming from your model. Now, the idea of the rejection sampling was that you find a constant, you come up with a distribution that's easy to sample from it, and another constant that upper bound your unnormalized distribution, and you do the sampling. So the main ingredients of the general algorithm you see in sampling approach that come up with the distribution that's easy to sample from and introduce auxiliary variables is there. But it's working for one dimension. It has its own limitation because you have to find this upper bound, and it's not very efficient. We talked about Gibbs sampling as an example of algorithm that use the structure of the graphical model. The vanilla version of that is that you sample one variable at the time, so your random walk in the space looks like this. And we said that if you run it long enough, it's going to converge to stationary distribution. That this stationary distribution is the distribution you want to draw a sample from. We mentioned that the ingredient for this Gibbs sampling is that you have so you don't have to condition with respect to all of the variables. You only need to condition with respect to your for every node with respect to Markov blanket. That in undirected case, it's very simple. All of the nodes that are directly connected to you, and this is Markov blanket because if I condition on that, I'm disconnected from the rest of the world. And for Bayesian net, it's relatively simple because all of so for every node, it's going to be all of the parents and all of the children, all of the co-parents of the children. And if you manage to compute this conditional, then you're good. You can easily implement the Gibbs sampling. So the main ingredient is that you don't need to, although we show it as conditioning with respect to all of the random variable, all you need is with respect to your Markov blanket of each of the nodes. And then we said that, okay, we should be able either to approximate this normalization for each of these conditional either in the closed form, or we know something about the distribution that you can approximate. So for example, in rejection, if you're using one dimension at the time, rejection sampling can be used to, even if you don't have 1 over z. The good things about it is that it's very easy to implement. It's just conceptually, it's just a couple of lines. If the model is conjugate, this 1 over z is easy to compute, and there's no rejection. You just don't, so it's pretty efficient. We extended this idea. We said, what if the model is not conjugate? I don't know how to compute this conditional distribution. Is there any general idea? We said that the general idea that also includes Gibbs sampling is the idea of Metropolis-Hastings algorithm. That the idea is even the implementation of that is also very simple. The idea back then was that you have a distribution, let's say Q, that you sample from it. You plug that into your unnormalized distribution, and you compute a ratio that was acceptance ratio. That if your proposal is symmetric, it boils down to basically ratio of the new proposed sample versus the previous one. If it's bigger than 1, you definitely accept it. So it's exploitation. And if it's less than 1, you accept it with the probability of the ratio, which is exploration. So it has a balance of exploitation and exploration. But we mentioned that Metropolis-Hastings, it's too general. It's like usually when you have algorithm which is too general, there should be some catch somewhere. And it was too general, so easy to implement. The idea was that if your proposal it has to be too local, and if it is the variance of the proposal distribution is gigantic, you can have very long walks, long jumps, but the problem is that the chance of acceptance is low. So you end up with very local jumps, and that means that it takes forever to explore the entire space. So that's a good segue because now we can talk about a better algorithm that allows you to explore the space in a more efficient way. So that's the topic of discussion today that I'm going to talk about, Hamiltonian Monte Carlo. So, all right, we also talk about this detailed balance. So we said that you have to come up with a proposal distribution Q, and we have to come up with the acceptance function F. You are free to propose whatever you want, as long as it satisfies so-called detail balance. So, so Q here is your proposed distribution, and this is your basically this is your previous point, the proposed point, the probability distribution that you're drawing sample from, and acceptance function, which is the function of the previous point and proposed point. And the idea of this detailed balance is that your path is kind of symmetric. It's like you can go from one point to another one and come back. So it's not directional. You can go back and forth. So if I actually think about it in an intuitive sense, that's what detailed balance means. So other than that, it's basically so much of the literature of the Metropolis-Hastings in the applied field is that you come up with an acceptance function and proposal distribution that's good for your specific model, because it's just like the condition that has to satisfy is very, very loose, is very easy, is relatively easy to come up with different F. So it's up to your creativity how to come up with a proposal distribution and an acceptance function. We talked very little about practical issues for MCMC. We mentioned that, well, the idea here is that you come up with a proposal distribution, you draw sample from it, and a stationary distribution of this is a density that you actually want to draw sample from. But we don't have any theoretical way to show that we have actually converged. So what people do is that people let the chain run for a long time, and they usually run multiple chains at the same time and have some measures of diagnosis. For example, one way of doing that is you have some held out data that you're not using during your random for Markov chain, and you monitor the likelihood of the held out data. So if the model is a good model and it's learning, you expect the likelihood of the held out data goes up and saturate. This is very much similar to the idea of the train test validation that we use in classical machine learning. But that's not the only way. So this is why I uploaded these couple of pages from Andrew Gelman's book that he has a lot of very practical, very useful tips on how you can diagnose if your chain has converged or not. So one of the ideas is basically, let's say that you want to monitor the convergence of the variance, a parameter, let's say variance, one-dimensional. So you basically plot the trace of convergence of that variable. So this is, let's say this is the iteration, and this is the samples from that gamma, that parameter, and you monitor it. So we usually discard the first phase as so-called burn-in. So we discard it because we assume that it hasn't explored the space long enough. So let's get rid of it. That's called burn-in. And after that, we draw a sample. Like let's say like every 10 variable, we start sampling from the distribution and pretend that those are IID. And then we can do several things for diagnosis. For example, we can monitor, assuming that, let's say 1,000 iteration is enough, or 2,000 iteration, or 5,000 iteration is enough for burn-in. You can monitor the distribution of 7,000 to 9,000 and 9,000 to 10,000 to see if it is converged to stationary. You don't expect this distribution to be vary from each other, so you can perform different statistical tests to do that. We also talked about that from computational point of view, there is a balance between how long you run your algorithm, because you have to let it run long enough that it explore the space, explore the entire space. But if you take it, what if you just explore the entire space, you're just wasting your computational resources going back to the same places. So you don't want to let it run too long because it's a waste of time. So there should be some sort of like a balance between, you have to make sure that it's running long enough that explore the entire space, but not too long that you're wasting your time. So one of the ways is that people run multiple chain at the same time. So running multiple chain also allows you to, if all of them converge to roughly the same distribution, you say that, okay, I started from different seed numbers, they're all tell me the same thing, I'm confident about it. So these are some practical issues about MCMC. So the big picture of approximate inference with sampling approach is that we come up with a distribution that is easy to draw sample from. In the very first section of the book last week, I talked about what if we just have one proposal distribution, like vanilla version of the importance sampling, but nobody has told me that I can change the proposal distribution per point, and that's the idea of Gibbs sampling. That's the idea of Metropolis, because you can adaptively, you can have a proposal distribution which is adaptive with respect to a point. And Gibbs distribution is an example of that, because your proposal distribution is variable I given the rest of the variable, and so you're changing the proposal distribution as you walk through the space. Another idea, the reoccurring theme in sampling approach, is introduction of this auxiliary variable. You saw examples of that in the context of rejection sampling, that you have one variable that decides that should I keep this sample or I should not. Another example, you also saw that in the context of Metropolis. We have acceptance ratio, that should I accept this sample or not. This is a reoccurring theme, but you can be more creative in coming up with auxiliary variable, and this auxiliary variable helps you to explore this space. We are going to see an example of that in the following slides. We mentioned that for high dimension, it's difficult. You saw that, for example, in the context of importance sampling, it was difficult. The variance of the weight explodes. So you have to use the structure of the graphical model in order to avoid this explosion. And in none of the methods that I introduced so far, I use the smoothness of probability distribution. Because let's say that if you have a probability distribution, although you don't have the normalizer, but you don't have a normalizer for that, but to study the smoothness of the probability distribution, you don't care about the normalizer. So if one area is flat, so if I have a distribution that looks like this area is very flat. Why should I draw so many samples on it? Why should I waste my time? So it makes sense to use the gradient of the P to help the sampling. So that's basically the idea of the two methods that I'm going to discuss today. Use of the auxiliary variable and using the using the gradient of the px. So I'm going to start if there is no question.
So after you burned in, is there a reason that you sample like 1 every 10 as opposed to just like bootstrapping from that data or something else?
Well, that's a really good point. So the problem here is that when you are doing, for example, Metropolis or Gibbs, sample number T and sample T plus 1 are not IID because dependent on the previous one. You can use bootstrap, but I'm just giving you very conservative way of doing that. So I'm just saying that the dependence between them decays, right? So T and T plus 1 are very dependent, but T plus 10 are less dependent. So you can pretend that, but you can use bootstrap. Yes. So you can totally use because one way of doing that is that if you run multiple chain and you want to see, give me let's say that posterior mean of this parameter that I'm really interested in. So you have to estimate it. Either you have to compute the mean, just like average them, and you just compute the bootstrap and then compare them from each other. Yeah, you can totally do that. Any other question? Okay, let's get started. So both of the methods I'm going to talk today is in a context of introducing auxiliary variable. The first method is called slice sampling. Hopefully you see what we call it slice sampling, because it basically boils down to cutting the distribution into vertical and horizontal lines. And the idea of the Hamiltonian Monte Carlo, it's very creative way of coming up with auxiliary variable that is it's basically the idea is coming from physics, and it's very successful algorithm. And I would say nowadays I'm going to introduce you the vanilla version of that, not all of the details, but very worked out version of that is now the engine of so-called STAN, which is using the algorithm called no U-turn sampling or NUTS. Okay, so what is the idea of the auxiliary variables? So remember that so many of these inference approach, inference question boils down to approximation of some sort of expectation. So either you are interested in computing expectation of the posterior mean, or you are interested in computing some conditional. You almost always you can compute it, you can write it as an expectation, and just f changes from time to time. So the idea of the importance sampling is that I'm going to extend px and introduce another variable. Let's say here I'm showing it as a v, and px is just integration, so integrating v out. But the idea here is that these px, py, so I'm going to, v is something that is easy to sample from, and it helps me to draw sample from x. So I have two conditional that is px given v, which is v is my auxiliary, and the idea is that I have to come up with a v. It's completely fabricated random variable, but I have to design it in a way that px given v and pv given x is easy to draw sample from. So why is that? Because if I start from some x, I can generate v because this is easy to draw sample from, and then given v, I can draw sample from x, and then I can continue. That's the idea. That's the gist of the idea. And another idea is that by introducing this extra random variable, you make exploration of this joint space easy. So far it's very too abstract. I'm going to give you some examples of how it works. So again, this is nothing but the chain rule. So the joint distribution of the px y is py given x multiplied by px. I mean, of course, if I can sample from px, there is no point of doing this, right? If I can easily sample from px, why should I draw another py sample? So it's drawing sample from px is easy. But the general idea here is that this one is easy to draw sample from it. And when I want to draw a sample from px, so I have to compute px given y. And this is proportional to pxy. Right? Because this is base root, right? It's equality. If I don't know how to compute this, is proportional. And so I should come up with a variable that is y. I can easily draw a sample from conditional, and then when I want to draw a sample from the other side, I use some sort of like approximation to draw a sample from x. So y should influence x, and x should influence y. So the idea of the importance sampling, so one can view the slice sampling as sort of combination of the ideas from Gibbs sampling, Metropolis, and rejection sampling. So it has resemblance to all of these algorithms, but it is pretty effective for like very general cases. So it's similar to Gibbs sampling in a sense that it draws sample one variable at a time. Remember, that was the general idea of Gibbs sampling. Draw one variable at a time and then walk over all of your random variables in a graphical model. In some sense, similar to rejection sampling in a sense that it draws samples and it has a criteria to reject or accept a sample, but it is not as crude as rejection sampling, because the rejection sampling was that I'm going to multiply my Q with a gigantic number so that it includes my sample. Here it goes, the draw sample. So it's not that inefficient. it is also very similar to MCMC in a sense that the proposal is adaptive. So I'm going to tell you the general story of slice sampling and won't go through the proof of why asymptotically, if you continue this algorithm, you actually draw a sample from PX. I'm just going to give you the general idea and leave the proof for people who want to read about it to the proper references. But the general idea is follows. So X is something that PX is a sample that is a distribution that you want to draw a sample from. But the problem here is that this PX you don't have the normalizer, right? And this is why it's difficult to draw a sample from. So I'm going to introduce a new random variable called Y, that this Y, so the joint distribution of these two random variables is as follows. So remember that I only have P star or P tilde, let me call it star, confusion. So if the Y is between 0 and Px, which is unnormalized density, it's going to be uniform, otherwise 0. So if I have distribution like this, and I'm at the point X, and this is my P star X, I'm going to slice it here. And so there is no, so this is basically, this is my X, and this is, let's say, my Y. So there is no mass in this area, right? And there is no mass in this area. There's only mass in this region, right? And this is uniformly distributed. Very simple idea. Is the setup clear, how we draw a sample? So you propose X, and I look into P, unnormalized distribution. I say that I can sample Y from 0 all the way to P star X and draw uniformly from that. That's it. Is it clear? Okay. If it is not, so I'm going to play with this to come up with the algorithm. So if it's not clear, just stop me now.
Is the Z variable still normalized for PX?
Yes. So you may say that you don't have it. So, but you'll see how it works out. So, but okay, let me show that if I draw a sample from this, if I manage to draw a sample from this, although it's kind of cheating, I'm assuming that Z is there. I don't have it. So, if I draw a sample from this distribution and integrate Y out, the result is going to be the distribution that I want to draw a sample from. So what should I do? So what if compute this, right? What is this integral equal to? Exactly. So it's going to be 0 to P star X. And what should I write here? 1 over Z dy. And this is P star X Z, which is Px. Very simple, right? So if I knew Z, I should be able to do that. So now the idea is that, okay, obviously if I integrate Z out, it's as if I draw a sample from Px. So what is the general idea of drawing sample from this? Okay, what's going on? Okay, you want to...
Maybe you zoomed on the slide.
Okay. So given a distribution, can be multimodal, and I'm assuming that everything is 1D. So I'm kind of doing two slices, one horizontal slice and one vertical slice. So why am I saying one vertical slice, one horizontal slice? To draw sample from Y, I definitely need to have one vertical slice there, right? I need a slice like this. And to draw some, so this is basically, this is auxiliary variable, and this is my current point, right? So this is a uniform distribution, and this is equivalent of having a vertical slices. But, all right, so it seems that Py given x is not hard. But what about Px given y? So Px given y, remember that Px given u, here, u, is proportional to P, u, and x, right? Okay. So P, u, and x is the equation that I showed you here. So it says you shouldn't go, if y goes beyond px, I'm going to assign 0 probability to it. Is inside of that area is flat. So it's equivalent of having a vertical slice. Sorry, horizontal slice. So if I draw x, I draw uniformly from distribution that's has this height, gave me u. And then here I'm saying that it should be the drawing sample from x is proportional to pu and x. So basically that's proportional to I'm just writing the same thing that I wrote in the previous slide, slightly different. It's the same thing. I'm just saying that forget about the normalizer for a second. There is no mass outside of the area that's bigger than y. There's no mass. The problem is I don't know the normalizer. But anything is there, anything in this area has a uniform mass. So all I need to do is to uniformly draw a sample from it, except that there are some areas that has a 0 weight. I don't know that. So the trick is that if you can find these points, computing, because the mass is uniformly distributed, you don't care about the normalizer. You just stick these pieces together and uniformly draw a sample from it. There is no change in the distribution. So either you can compute this point of contact between density exactly. Good for you if you can do that. It's very fast. If you cannot do that, you do it numerically. And that's the entire idea of the slice sampling. So you have vertical slices to draw sample from auxiliary, and horizontal slices from to draw sample from px. If you manage to find this connection point exactly, great. It's just bunch of uniform distribution, drawing from uniform distribution. If you cannot find these points, we will do it in an algorithmic way. Is the idea clear? Yes.
Doesn't this break down in high dimensions?
I'm talking about only one dimension. So for higher dimension, we do something similar to Gibbs sampling. We do one variable at a time. But it's pretty effective. Because unlike things like rejection sampling, it's not as crude as rejection sampling. Rejection sampling say that I'm going to have a big pile over the distribution, and if because I don't know how to come up with that big pile, I have to make it big M or big K in that slide, and then the ratio is pretty bad. The ratio of rejection is pretty bad, and it gets worse and worse with the dimension. Here, I just say that I work directly with the profile of the density. I cut it, and then within each cut, I just do uniform, no rejection. So you will see that there is some rejection here because in most of the cases, we cannot compute these points exactly. We have to approximate. So, all right. So, is setup clear? Yes.
So, I mean, if you just want to find the area under the curve, because basically integration is just the area under the curve, why don't we sample interval instead of just sampling one point U.
What do you mean something? It's like a histogram?
So instead of sampling, just one point and then finding area over that line, instead sampling a smaller interval and then doing it over.
So that would be very equivalent of binning the X, right? So if I can bin the X and the exactly the same thing that you just said, it's like equivalent of that. So I'm going to bin the X and I'm going to end up with a bunch of bins. And then I'm going to first choose the bin. And then inside of the bin, I have to, because at the end, your result should be on X space. It shouldn't be bin index. So you probably either have to sample uniformly in a bin or things like that. So two problems. Problem number one is that how are you going to bin the space? If you want to bin the space, so you're binning the space should be somehow function of the curvature, right? If you have very steep curvature, you should bin it more. If you have a flat curvature, you should bin it less. So that ends up to quite complicated algorithm. Second problem is that you cannot just sample choosing the bins is easy, but choosing something in between is hard. So how do you choose? So you choose always the center, then your X always ends up to look like discrete. You have to come up with something within the area of each bin, and then you have to prove that if you draw a sample from this, you're actually drawing a sample from the original distribution. Yes?
How do you pick X?
Oh, you just like start with some initialization. Doesn't matter, because what you're actually interested in is drawing sample from X. So you draw a sample from, you start with some X, right? And you plug that into your P X star, right? Unnormalized version. You can plug that in, right? And so you get the value, the upper bound. So you say that, okay, the value of that is, I don't know, 10. You draw a uniform from 0 to 10, that becomes your U. Now it's time to go for the next. So this is basically xt, and then you have to come up with xt plus 1. You continue this, and you discard all of the U's, and that's your samples. That's the idea. Right? Any question? Yes.
Can we go over one more time how this approximates the normalized distribution?
Yeah. So approximate normalized distribution is that, so I'm introducing a Y distribution, a new distribution that's a U of Y notation, doesn't matter. But I want to say that if I integrate that out, so basically equivalent of, if I draw a joint distribution from Px and Py, and if I discard Y, it's equivalent of marginalizing out. Then the result is Px. This is why I'm computing this expectation. That's the general idea of all of this algorithm. I extend the space with another one. I draw sample from both of them. For whatever reason is easier, I'm going to discard the other. That's equivalent of, so yeah. Okay. So yeah, so that's basically what I was explaining. So it's like somewhat similar to the Gibbs distribution, Gibbs sampler, because we do one variable at a time. That's similarity with Gibbs sampler. And so we are drawing sample from U condition on X is easy because uniform. And drawing sample from X condition on U is also uniform, except that we don't have the normalizer and we don't have this point that touches the boundary of the Px. So how we are going to do that numerically? So I'm going to run some sort of like a simulated version of that for a very crazy distribution that has 1, 2, 3, 4, 5 modes. One of the modes, 2 of the modes go to the second floor. So what I'm going to do is that I'm going to tell you how it works. So I'm going to start with 1 point. So this is my starting point. Okay. So that's my, let's say, xt. So I'm going to plug that into Px star and get this, which is Px star. Okay. So what is the next level? Auxiliary, right? So the auxiliary is uniform between these two. I'm going to draw something from that. So here we go. So that's my auxiliary. Right? So the next step is that I have to cut through all of this. So I'm going to propose some cut because for whatever reason, I cannot solve this. I mean, if you could, great. Use that. But most of the time, we cannot. We cannot say that for every level set, what is the cutting points? It's the equivalent of solving a nonlinear fixed point of the, solving a nonlinear system. It's not always easy. Okay, so that's my interval. And you see that part of this interval is outside. So what would happen is that because I didn't find the boundary of this distribution exactly, so what I'm going to do is that I have to propose an x and evaluate the px to see, am I here or am I here? Okay, so what I'm going to do is that, so this is my extension on the right, this is the extension on the left. So I basically draw a random variable and say that my gut feeling is that the extent, so this interval is, I don't know, W on the right side and W on the left side. That's just my feeling. For whatever reason, I cannot solve it. It's hard. But I'm just going to propose some interval. Okay. Now, I'm going to draw uniformly from this interval. Oops, it fell outside. And it's easy to check, right? It's very easy to check because we just plug that into F. And you see that for this new x, which is xt plus 1, this is the value that you propose. And this is the value of xt plus 1. This is bigger, right? Your value is bigger. So I cannot accept it. Yes?
How do you sample xt plus 1?
This is uniform.
xt plus 1.
On this interval is uniformly. So from the interval, I said that I don't know the value of this interval. I have to find it basically numerically. That's what it boils down to. And when you say it numerically, you can say that I think this interval is, I call it, say, W. This W width on the right and W on the left. It's just something I propose because I have to find some guess and then shrink it. This is my guess. It was a bad guess because I draw a sample from it and it fell outside. So, okay, so this is not a good one. So maybe I can get rid of so apparently I have to get rid of all of this. So this was the right side of the interval, so I'm going to use this as the left side. So I'm going to cut that, and this would be my new left, my new right. Draw another sample. Okay, so this is inside. This is still has a little bit of approximation because I cannot visualize the profile. So I don't know this is outside, but it is approximately right. So this is inside because if I evaluate this is xt plus 2. If I evaluate this, the x star t plus 2 is less, so the xt plus 2 is here. My proposal is here, so I'm going to accept it. It's inside of the region. And continue. So sample the new one and go on. That's basically the skeleton of the slice sample. Clear? Yes.
So why do you need to sample one by one? So why do you need to do that recursively? So what if you just start a fresh new one and keep going?
Fresh new one on what?
X.
So remember that you are cutting on different direction, right? So you're cutting on a different direction. So you propose xt plus 1, xt, which was good, right? And then you have to go with t plus 1. The first t plus 1 that I proposed was this. And it was bad. So I have to go to so remember that the idea of the auxiliary sampling is that you want to get x and auxiliary, and you want to make sure that the x is valid, right? And then discard y. The x that I proposed here was pretty bad because it was outside of the distribution. And because I cannot, if I want to actually implement it, I cannot visualize it, right? So I have to propose something and check if it's outside of my distribution or not. Because remember, at the end of the day, what we are doing here is that we are sort of doing that integration. So we are saying that am I inside of it or am I outside of the PY? So you are doing implicitly this integration, and so you can start fresh, but you're not exploring this space. So the good thing about this is that because you are cutting on X line, you can jump between modes. You start new fresh. How do you explore the space? Any question? Yes.
So how do you initialize your guess for the horizontal slice and ensure that it
Horizontal slice. Okay.
horizontal slice? How do you ensure that it spans, for example, all the nodes in this distribution without being wasteful?
Without being wasteful. So I cannot make sure that so here's the problem, because I have to come up with a guess. And you're right, like this would have been larger to include this one too. But the problem here is that if I make it very large to make sure that I'm cutting all of the modes, then it's more likely to have intervals that look like this. Because remember, if you could have solved it numerically, great, you cannot. And you have to come up with something. So it's some sort of like a balance between, you can go with like a large jumps with a higher rejection rate, or you can go with a smaller jump with a model.
So you need, when you're sampling in the vertical direction, you need that to be uniform to get the correct scaling.
Yeah.
In the horizontal direction, you could presumably sample from the distribution of tails, like Gaussian, right?
That's right, but then the problem is that you px py, you have to prove that px py after integrating z, yeah, exactly. After marginalizing z out. This is very simple scheme that makes sure it's correct. It's not necessarily the best scheme. Yes.
I still don't understand why this does better than rejection sampling, especially if you have a lot of peaks and they're very narrow, like in the space. You're going to get a lot of rejections.
Yeah, but the good things about this is that because it goes vertical and horizontal, can cut through multiple peaks. So it has a chance of jumping from one peak to another peak to another peak. Rejection sampling doesn't care about peaks. The rejection sampling says that give me one distribution that's so gigantic that includes all of the peaks. I don't know how it looks like. It's just an upper bound, right? And remember, you cannot compute. We had this px k qx, right? I don't care how many peaks it has. You just give me k big enough that it is less than 1. Because you want to make sure that py given x is valid. Remember, this was py given x in rejection sampling. Give me gigantic q that includes everybody. I don't care about how you jump between it. This is not what I get. So this is actually working directly with px star and allows you to jump between modes. You are right that, yes, if you make it bigger, you have a higher chance of visiting all of the modes, but because you cannot visualize it, you don't know you should be very conservative, or so it's some sort of like a trade-off in between. So the idea of the implementation goes as follows. Okay, I can spend 2 minutes. So idea of the implementation is as follows. So I sample, so the ingredient is that my current point xt and the interval associated with it. So I have xl left side, xr right side of the interval. I have to come up with this interval that encloses my xt, and then I have to expand this interval until I'm outside of the boundary of the px. And then sample for x, and then correct, either reject the sample which results in the adjustment of my interval, and continue. So this is basically the skeleton of the slice sampling. So how you are actually implementing sampling from U is very easy. You just plug that into px, uniformly sample from it. Sampling from sampling the interval is basically what I just explained. That you have to come up with a guess, and your guess is R. R was this, like, go R to the right and go R to the left. And then if you draw a sample from it and it happens to be outside, you just shrink it. So this is basically the shrinkage step. And so you just continue with the same idea that you draw x uniformly within this interval. If it happens, yes.
What is W here?
So W is a width. It's the initial width.
Isn't that R?
No, the
Yes.
so let me see. So W. So W is basically the upper bound for your guess. So if I choose W, which is gigantic, I'll become less conservative. If you can make W small, it'll become more conservative. And R is your guess. Okay, so that's the idea of the slice sampling. So how can I do that for multivariates? Again, what we just said in the beginning, we do one variable at a time. Fix the rest of them. Fix the rest of the variable is just going to be a function. We don't care. We can evaluate it, right? And we sample from X using slice sampling and continue. So in that sense, it's very similar to Gibbs distribution. And all I care about is I should be able to compute something which is proportional to this. And of course, so in Gibbs sampling, we needed to compute this exactly or approximate it very quite accurately. But here it doesn't care because it directly works with the PX. And that's the general idea of the slice sample. So all of this that we did for the slice sampling was that we introduced new random variable that allows us to explore the modes and have a bigger jumps. Over the past years, another algorithm got a lot of attention, and I would say it's probably state of the art, called Hamiltonian Monte Carlo, that introduced another auxiliary variable that allows to explore the space very efficiently. Up to maybe 10 years ago, people knew about this method, but they had some reservation because Hamiltonian Monte Carlo had a lot of parameters to tune. I'm going to introduce the idea here. But there has been a leap since perhaps I would say 2014 that people come up with the schemes that fine-tune the parameter of the Hamiltonian Monte Carlo and make it very efficient. So nowadays, if you work and use the stand that under the hood is using HMC, it chooses many of the variables for you efficiently and provides great diagnosis too. So I'm going to introduce the idea of Hamiltonian Monte Carlo. So let's say that you have very weird distribution that looks like this. This area of the red that I'm showing here is area of the high probability. So you see that it's very strange distribution, and you have low hope to compute the normalizer for this. So if I use Hamiltonian Monte Carlo to propose a distribution for every point that I am inside of this typical set, I'm going to call this typical set, or the areas that has high probability. If I have a high variance, because the entire distribution lives on a very thin shell, if I have a high variance, I end up jumping outside of this thin shell. So I end up rejecting the sample with high probability. If I have small variance proposal, I'm going to accept the probability with a higher chance, but I'm going to move very little. If I'm here, I'm going to move very little. So this is the problem that we are facing with in many of the cases, that the set that has high probability has some sort of a manifold structure. And the problem is that if you want to walk randomly on it, so big variance, bigger exploration, jump outside, you reject the sample. Small variance, you accept it, but you move very little. So you need gigantic number of samples to explore the entire sample. And that's the problem. But then you look at this and say that this is pretty smooth. Why shouldn't I use the smoothness of this PX to help me to walk through that? And that is the idea of the Hamiltonian Monte Carlo. So you want to get sample that looks like this. Start from outside as soon as falling inside of the area with the high probability, stays in it. And it's explored the entire space. So the optimal trajectory should look like something like this, that you start from inside of the set and walk through the set. So you need some sort of something to help you to walk through this set efficiently. So the intuition of that is coming from physics. So to walk through the entire set, we need some sort of like a random vector field. That this vector field in every location of the set tells us where to go. Right? So this is the idea of the vector field. Every location that I am, I can read the vector field and say that go along this direction. So what that vector field should be. So basically the challenge is that how can I come up with this vector field that helps me to explore this space in a more efficient way. So the idea is coming from physics. So let's say that there's a satellite orbiting Earth, and so if the satellite is just there, stationed in one location, the vector field that we are dealing with is a gravity, right? So all it does is that the satellite is there, is going to absorb it toward Earth, and going to crash on the Earth. So in order to make sure that we are exploring all of this area of high gravity, we need something else. So what do we need? If the satellite is just there without moving, it's going to crash to the Earth. What do I need to make sure that it doesn't crash on the Earth? Exactly. You just need a momentum, right? Because otherwise it's going to crash. And you need a right amount of momentum, right? If you give it too much momentum, it's going to run away, right? It's going to get further and further away from Earth. You need the right amount of momentum to make sure that it explores the space. So the vector field that you're looking for is not this, but it looks like something like this. So, and this is the idea of the HMC. Every particle that you have has a position and also has a momentum. And this momentum makes sure that it doesn't go to somewhere station that gets stuck there. It explores the area that has a high potential. So remember, this is the slide that we had before about the idea of the auxiliary random variable. So I'm going to change the notation a little bit, and instead of p, I'm going to use pi, because I want to use p for something, for momentum. So pi, by pi, I'm talking about probability distribution. X is the position of your random variables, all of your latent random variables that you want to use for exploration, your latent random variables, and p is the momentum of those. So effectively, what we do in HMC is that you have, let's say, d-dimensional representation, which is your position x. You multiply that with another, so you just extend the space, you make it twice big. If it is d-dimensional, it's going to be 2d-dimensional because each of these has a momentum. And but again, the same idea. So chain rule, so we want to have something that x, which is your original things that you're interested in, is influencing auxiliary influences x. Okay. So what is the idea here is that the idea here is we build a Hamiltonian system. That in the Hamiltonian system, I'm not going to make it like a physics class, but we have kinematic energy and we have a potential energy. So remember that satellite example. The momentum that we give to this satellite is basically the kinematic energy. And this area of the red area that I showed around the Earth was the area of the same potential. So you want to make sure that area of the same potential is explored. So how do we define this? We define the Hamiltonian as a minus log of the probability of the joint distribution of the x, which was whatever that we were interested in, and its momentum. And if I expand this, so I'm going to define a kinematic energy which is the conditional probability distribution of the auxiliary variable given on the location, and potential energy, which is the minus log value of the probability density that we were actually interested in. Right? So the potential energy is only function of the probability density that you want to sample from, and your kinematic energy is basically the extra property that we give to the system to make sure it doesn't crash. So another cool thing about this is that, remember, if you don't have the normalizer for this, log is going to get rid of it, because it's going to be pi star minus log z is going to be some constant. And you can design the kinematic. So this is your degrees of freedom. Remember, in your Gibbs sampling and Metropolis, you have a Q as a degree of freedom. Here is your degree of freedom, because this is specified by your model, right? This is log of your model. This is your degree of freedom. You can design. You have to design it properly. So as I said earlier, we have. So we call the minus log of our model, we define as the energy, as a potential energy. And we use the gradient of that to help to walk in the space. So our random walk is going to be walking through the space. And so the idea is that we want to explore all of the areas with a high probability. So to give you very little background about Hamiltonian Monte Carlo, so it has a lot of application, probably ubiquitous in classical mechanics, in modeling n-body simulation and fluid dynamics and modeling the galaxies. So the Hamiltonian is the total energy of the system, which is, roughly speaking, is the potential energy plus the kinematic energy, and we want that to be preserved. Oh, yeah. And it also has an interesting property that is dynamic, is reversible. Remember, the reversibility was the thing that we needed in detail balance in Hamiltonian in our algorithm before. Okay, so what is the Hamiltonian dynamic? Remember that we want to come up with that vector field. So what is our vector field right now? So we are going to give this is a dynamic system that is so if you start with xt, is going to have a dynamic. So, and the dynamic of this system is governed by the Hamiltonian system. So the dx dt, which is x is your position that you want to explore in a space, with respect to time, is partial derivative of your Hamiltonian. So if you think of x as a position, what is this? What does it act like? X is your position, and derivative of the position with respect to time is more like a velocity, right? So derivative of the kinematic with respect to this auxiliary variable acts like a velocity. And to update your auxiliary variable that here I'm introduced as a p, so the derivative of the p with respect to time is going to be derivative of the k, which is your kinematics, and derivative of the energy. So if you think about it, this was the gradient of the system, and this is kind of of the correction term, if you want to think about it. So if we didn't have this term, we would have arrows that look like this. So remember the Earth and arrows look like this. If we only have energy, the energy, so the arrows of the energy is going toward Earth, because that's a potential energy, right? So this is the extra terms that make sure that we don't have the vector fields like this. That's the big picture idea of how this Hamiltonian makes sense. It works. So now this is a dynamic system. I have dx dt, which means that if I can integrate it out and find out when x and p is going to look like an iteration t plus 1, t plus 2, and so on and so forth. Make sense? Yes.
So you have to tune this correction gradient very specifically so that it corresponds to the curvature of your.
Yeah, that's a really good point. So This is your degree of freedom. You can design K however you want. So there are a lot goes into this, but let me give you the general idea. So you want to come up with a K that has good convergence properties. Because at the end of the day, we do have some sort of acceptance rejection here. So you want to come up with a K that explores the space and has low rejection rate. It turns out that actually Gaussian distribution is pretty good. And what is happening inside of the stand is it's some Gaussian with some variance. So what they have inside of that is K is not even, I think it's not even dependent on X. It's P. So you should see that in the next slide. So show it. So one way of doing that is a very simple way of doing that is that I know that I can have a K which is dependent on X. I'm going to make it only dependent on P, which is going to be norm of T divided by 2. This is equivalent of having a norm, having a Gaussian distribution with the unit variance. What is happening in reality is that people usually implement it as P transpose M P. And that M is like can viewed as an inverse covariance. And they change it with the space. But this is the vanilla version. That's your choice. It's a choice for KP. Make sense? But you can come up with other stuff. So what does it mean for what this kinematic does in reality? So let me simulate one for you. So let's say that this is pi x. Yes.
Does EX define our distribution?
Say it again.
Does EX define our distribution?
Yes. So but it's unnormalized version. This is a log of the px. So,
and we are introducing KP. It's a free variable. We can change it as we
Phi value?
free variable.
Oh, free value. Yes, yeah, exactly. So your kinematic is something that you design. So you say that this is how my system is going to behave. Yeah. So let me tell you how it works. Pi x was, so let's say that things are one-dimensional because otherwise I don't know how to visualize it. So x is one-dimensional. So I want to draw a sample from pi x. So it's going to be some distribution. So I'm going to introduce an auxiliary variable which is as big as x. So here x is one-dimensional. It's going to be extra dimension. So, and similar to what I explained in previous slide, I'm going to make P, which is coming from normal distribution and unit variance, which is equivalent of saying what I was saying previously, right? As if I'm drawing sample from N1. The same thing. Okay, oops. So the joint distribution is going to look like this, right? The cloud. So what I'm going to do is that I'm going to start with 1 point. Let's say I'm going to start with 1 point here. I'm going to sample from P, from pi px. So I'm going to lift it up to two-dimensional. So this is what I start from. I'm going to lift it up and follow the trajectory of the, follow the kinematic of the Hamiltonian space up to, let's say, 10th step or something, right? For some fixed amount of time. So my point, which was here, and I lift up to 2D, I follow the Hamiltonian and end up here. So I'm going to discard U, and that's your new point. And that's the general idea. But the beautiful things about this is that it allows to have a gigantic jump. I went from this side of the distribution all the way to the other side of the distribution because of the properties of Hamiltonian. So, and next point is that, again, you draw another sample from P. So this is going to take you somewhere else. Let's say here. So you lift it up. So this is going to be your xt plus 1, another P, t plus 1. You follow Hamiltonian. End of another place. So you can think of it as there are level set of the potential energy, right? P going to jump you from different level sets. Hamiltonian takes you to another location. So you explore different levels of the distribution this way. So now the question is that, okay, so there is something complicated about this, is that this is easy, so I can come up with some KP, and you saw that even simple KP works pretty well. But in order to come up with the next point, I have to solve this Hamiltonian, I have to solve this integration. So there are different methods to compute this integration, Euler method and leapfrog and so on and so forth. The challenge here is that, so we are going to talk about leapfrog because of its nice properties. So the actually implementation of the leapfrog, which is this integration of this Hamiltonian system, is extremely simple. It's basically 3 lines of code. So I have to update my momentum with, so let's say that my step are epsilon. So I'm going to do half of the step on moment, update my parameter, do other half of the step on the moment. So this is my first half. This is my first half. Update the position, update the second half. Although it looks very simple, it is very effective for systems, for Hamiltonian system. So if I show you the behavior of this integration, most of the most of the methods for computing this integration tends to drift off, because remember, you want to go through the entire space of the same level set, right? So because of the numerical integration, other method tends to drift off, while Hamiltonian approach drifts drift a little bit, but go so it's basically vibrate around the actual level sets. And that's a really good property of the leapfrog algorithm for this integration. That's why it's what is actually implemented for HMC. There are theoretical reasons for that, but I'm not going to go through that.
Is there a reason why you would do 2 steps instead of 3 or 4, maybe get more accurate?
Oh, so this is basically, okay. So the integration that I told you was going from here to here is just one step. You can run it for n step. Yeah. So that's the parameter. I'm going to talk about that in a second. But basically what I explain here, just one step of the leapfrog. So you see that I'm going to go L steps, right? So tau is like the steps that I have to go. So you can do, actually this is one of the parameters of the HMC, that how many steps of the leapfrog you're going to run. Okay, so and you see the behavior of that for different methods. You see that Euler approach drifts up quite a bit, but for a small step of the modified version behaves slightly better. But anyway, so the leapfrog, which is very easy to implement, is much accurate than that. And even if your step size is crude, it's pretty good. This is very crude step size. Still works pretty well. So this is why it's preferred. So this is basically the gist of the Hamiltonian Monte Carlo approach. You have to introduce the kinematic. Most of the time, we have very simple kinematics like Gaussian or Gaussian with some variance. And we just run the Hamiltonian implementing leapfrog, and here you go, it works. So if I want to write the general idea of the Hamiltonian algorithm, you sample from the, so I think that you run it, I showed you the dry run, how it works, and you sample P from your kinematic. You run Hamiltonian step for L step. And then, because there are some inaccuracy at the end of the day introduced into your integration, you do the same thing that you do inside of the Metropolis-Hastings algorithm. So here, by phi tau, I'm representing this numerical integration because I didn't want to write it. I want to write it in an abstract sense that this is your, after doing the numerical integration, which is this guy, so you compute the probability of the new point versus the past point, and you accept or reject it. That's it. Now, there are choices here. So the choices are, how can I design the kinematic? How much my steps length would be, and how long I have to run it. And these has been the problems in HMC maybe till 10 years ago. Nowadays, people have studied quite a bit, and there are schemes that they can find out, based on your model, they can find the optimal epsilon and optimal tau for you quite well and give you very accurate results. So give you an example of how this behave in reality. So Hamiltonian Monte Carlo, it results in much bigger jump. So if I show you the results of the algorithm, let's see if I have it or not. So my Metropolis results going to have a local jump, while if I draw the path of Hamiltonian, it looks like crazy. It just goes from one end of the distribution to another end of the distribution. So explore the space much faster. So I have one demo here that, if it works, so yes, so this is the result of Metropolis. Oops, working. Okay, so it started working. So you see that it's exploring the space, but the jumps are very local. This is basically x coordinate, x coordinate, and y coordinate. See that it's very local. After a bunch of runs, it finally explored the entire space. And this is the result of, so I don't show you the Gibbs sampling, and this is the result of Metropolis. You see that it's very fast. It jumps through the space much more effectively than. So you, basically what it means that you have to run it for much less time than Metropolis. Okay, so that's kind of what is implemented in the STAN algorithm. Inside of that is is HMC algorithm. But after this paper in 2014, they have worked out how to come up with the best parameterization of step size and the lengths that you want to run the algorithm. So to summarize, MCMC algorithm are very general purpose. MH, for example, does not even care about conjugacy. You can have very, and it's very easy to implement. So if you are in science and you have a model, you don't want to be limited by the conjugacy. You just want to write your idea in a generative story and run it, and your model is not big, you should definitely consider running sampling approach, because it produces much better result in terms of it's not overconfident about the values. It has a good theoretical guarantee asymptotically, although we have some issues in terms of like we don't know where it converges, but I didn't talk about it that much. Nowadays, we have a good grasp. There are a lot of good diagnoses. Overall, is significantly slower than variational approach. Variational approach, if you have a gigantic model, I would say still you cannot run this for MCMC unless you come up with your own fine-tuned algorithm that exploits the structure of the model. And there are quite a bit of parameter design choice, although I would say with HMC and STAN nowadays, it's a big advance. Yeah, that's it. Thank you.